Good morning, everybody. Today we're going to discuss the last part of quantum physics, and that is the wave-particle duality. Learning objectives are: what do we mean by the wave-particle duality? We describe the main points of the Broglie's hypothesis that matter particles also have wave-like nature. And we state the use of the equation lambda is h over p, which equals to h over mv, and we describe evidence for the Broglie's hypothesis. Now, we have seen that photons are quanta particles of light, and electrons being diffracted, a property of waves. Monsieur Prince Louis de Broglie, he said electrons should not be only considered as particles, but also as a frequency that can assign to them. He suggested that the particles such as electrons might also show some wave properties, and he summarized the Broglie wavelength lambda was given by lambda equals Planck's constant over the momentum of the particle, so that is Planck's constant over the mass times velocity. Now, what he, in his formula, he suggested that the wavelength can be altered by the change of the velocity of the particle. Yeah? So it depends on the momentum. So the Broglie wavelength is the Planck's, we have to put lambda by the way, wavelength equals to the Planck's constant divided by the mass times velocity. Okay. Now, it's interesting to know that actually you could calculate your own Broglie wavelength. For example, you're a person 65 kilograms running at a speed of 3 meters per second through an opening of a width of 0.8 meters. So, according to the Broglie equation, the wavelength of this person could be lambda is h over mv, lambda is 6.63 times 10 to the negative 34, divided by the mass times the velocity, and you would get actually a wavelength of 3.4 times 10 to the negative 36. Yeah. Now this wavelength is really small, yeah, and especially compared with the size of the gap. So we will not get any diffraction, which we will talk about now. Okay. And I want to show you the diffraction of the tube experiment. When we look at the tube experiment, on the left side, we have a supply to the filament. Yeah, the filament glows and releases electrons, and over the electrons we have an anode and a cathode with a very high voltage, 5000 volts. So that means that the electrons are accelerated, they will hit a carbon disc, and then these particles will hit at the end a fluorescent screen, and we're going to look what is going to happen. Okay.
So this is equipment we can use to look at electron diffraction. What we have over here is an EHT power supply which goes up to several thousand volts. We then have a very kind of delicate glass tube. These cost about £700. At the back we have a spot which you can just about see is glowing. And here we have the thermionic emission of electrons. Next to that we have an anode, which is this kind of cylindrical piece of metal which we hold at a high voltage to accelerate the electrons. And then in front of that, you can just about see in this kind of metal grid here, we have a very thin piece of graphite. And because of that crystalline structure, what that's going to do is it's going to hopefully diffract these electrons. Now, the electrons hit the screen over here, and they then cause an emission of light. So we don't see the colour of electrons, because they're colourless, but what we see is where the electrons land, we see a little green spot. Now, if we turn out the lights, now as we increase the anode voltage, what this does is that it increases the kinetic energy of the electrons, and that means their momentum increases, and therefore their wavelength decreases. And what we see forming on the screen are these concentric circles, okay? And these concentric circles are the diffraction pattern caused by the electrons moving through the graphite and being deflected. So this is a really nice example of showing this kind of wave-particle duality.
So what we see at the end of the tube, I hope it's a little bit clear, but you see a clearly diffraction pattern. Now this actually proves that electrons can behave like waves, okay? So here we have the wave duality particle, okay? Okay, summary of the experiment. Beams of electrons are directed to a thin piece of graphite. Then rows of atoms cause the electron to beam to be diffracted in certain directions only. So what we see, we observe rings due to the electrons being diffracted by the same amount from grains of the diffraction orientation, at the same angle to the incident beam. In 1927, Davidson and Journer confirmed this prediction with the experiment using electron beams. They actually used a nickel target instead of a carbon one. And the wavelength they measured agreed exactly with the Broccoli. So there is a relationship between the accelerating voltage V and the kinetic energy of the particles. Remember, the wavelength depends on the Planck's constant divided by the mass times the velocity. So the velocity is related to the kinetic energy of the particles. A little bit about the electron volt again. I discussed it the last time. So the amount of kinetic energy by a single unbound electron when it accelerates through an electrostatic potential difference of 1 volt is, remember, energy is charge times potential difference. The charge of the electron is 1.602 times 10 to the negative 19 times 1, and that is 1.602 times 10 to the negative 19 joules, which equals to 1 electron volt. Now I give you this question, so I would recommend you to pause the video, try to make the calculations. For the first question, find the wavelength of an electron with a mass of 9 times 10 to the negative 33, moving at a speed of 3 times 10 to the 7 meters per second. In the second, find the wavelength of a cricket ball, mass 0.15, moving at 30 meters per second. And in number 3, it is also desirable to be able to calculate the wavelength associated with an electron when the electron voltage is known. There are 3 steps in the calculation. Calculate the wavelength of an electron accelerated through a potential difference of 10 kilovolts. Pause the video. For number 1, the kinetic energy is E times V is 1.6 times 10 to the negative 15 volts. In step 2, EK is half mv squared equals to half mv squared, so that's P squared over 2. So the momentum is root 2 MEK, and then you will find for the momentum 5.4 times 10 to the negative 23. And we can calculate the wavelength, which is using the Broccoli wave function is 1.2 times 10 to the negative 11 meters. That is about 0.012 nanometers. Probing matter. Now, as I said before, all moving particles have a Broccoli wavelength. So, the structure of a matter can be investigated by the diffraction of particles. And we are talking about the structure of metals and even the structure of DNA. Yeah. Normally, the diffraction of slow moving neutrons, 10 to the negative 10 meter, is used for the arrangement of atoms in metals and non-metals, but we also can use electrons, as you will see in this picture. That is the electron diffraction pattern of pure platinum. In the book you will see on page 482, you will see the electron diffraction pattern of an alloy of titanium and nickel. Yeah, as said before, you can also look at page 483 and you see actually the structure of the giant molecule DNA deduced from the electron diffraction. So, just one note on the electron diffraction. Remember, you can actually accelerate the electron, so you're going to change its momentum so that their wavelength is similar to the spacing between the atoms. Okay. Now, in conclusion, the nature of the electron wave particle. The electron has a dual nature, just like electromagnetic waves. The duality is referred as the wave particle duality of the electron. In simple terms, an electron interacts with matter as a particle, and we have seen that in our Newtonian mechanics. An electron travels through space as a wave, and this comes from the diffraction of electrons that I showed you with the tube experiment. Okay, this is the last part of chapter 30, so you will be able to make end of the chapter questions. Please make end of the chapter questions before Thursday, so we can discuss all the questions and then we move directly on with nuclear physics.